Okay, so very good morning. And what is it that we were discussing in the previous class? Backpropagation. So let me quickly draw that diagram for two layers and then quickly summarize what we did in the previous class and hopefully complete that in this class. This is my R-1 layer, for example. And then I have another layer here. This is the whole summation that you are doing, followed by activation function. This is the rth layer. Summation, activation function. Let us assume that they are K subscript R such neurons are there. Okay, so each one from the R-1 layer will get an input here, and of course there will be some this W0 is there, no? Bias function is there, that also we will give as an input here. Of course, same you could draw here also. Now we were calling this rth layer. So let's say if you look at here, the output at this point before you give it to activation function, representing it by the letter V, it is in the rth layer, superscript R. Let's call it as the jth neuron. So let us call it as V subscript J of R here. And let's call this, whichever you are getting here, output is Y for an rth layer for a jth neuron, YR of J. Okay. So essentially the function we are looking at is dou J by dou W bar. And if you are looking it for an rth layer, you write superscript R here. And in that, if you are looking for a jth neuron, you represent it as subscript J. And of course, each of them would get from K subscript R-1 neurons, the weights will be there that you could use as the another letter there if you want, right? See, the way we did the derivation for this is we have cleverly written that from essentially the factor that you would like to play with is this W, correct? And this J is your cost function. You do such that this cost function is minimized, you are going to vary your W. That's the basic idea. The way we have written this is, of course, J is written as some summation of all n samples E of I. Your I is varying from 1 to n. So error you are calculating over all of them. See, the relation of W bar, if you from E of I to here, so I could write here dou E of I. So essentially dou J will eventually convert to dou E there, correct? So dou E of I over W J R bar. The way we have cleverly written is till here, and because this in terms of W's is very clear to deal with, because this is previous layer, whichever number of inputs are number of neurons here, and the weights are coming from here, in fact. So that is easy to make the derivation there, is it not? So that's why this has been written as dou E of I by dou VJR we are writing. Jth layer, rth layer, jth neuron into dou VJR by dou WJR bar. That's the clever thing that we did. Then this is still has to be figured out, not a straightforward thing. We have not yet done that. This is again, you could write it as, for example, delta JR. On the other hand, this is easy to handle. Okay, how is that easy to handle? VJ is nothing but W1 times this input plus W time 2 times this input and so on plus W0 with all the subscripts and superscripts. You are taking a derivative of this here with respect to W itself, right? Each one, it's again a vector there. What will happen now? W1 y1 plus W2 y2 plus W3 y3 plus W0 is there. If you are taking with respect to W1, all you will have is y1, okay, the one which is coming from here, this neuron here. So that is why eventually what you got here, this one 1, because W0, the multiplication is 1 there. Next time with W1, if you are taking, what will happen there? Y, where is the input coming from? R minus 1th layer, R minus 1th layer there. And of course, you could write I because the summation is there for each one you are getting there. Okay. And anything else? What is the neuron number there? 1. In the R minus 1th layer, 1 is there. Okay. And so on. The last one will be, what is the subscript here? How many neurons are there? Very good. K subscript R minus 1, and that's R minus 1 of I. That's all. Whichever all we have discussed in the previous class. If I don't have to go so formally, this is what we are getting here. This is nothing but all the outputs here are here, just concatenated with 1. This one is coming from this, whichever the bias value you are giving. That's all. Is it clear? Why we arrived at that particular result in the previous class? Good. So this, we are calling it now, let's say I put it as, this is what, keep it in mind, this is something we are representing, defining ourselves to call it for a easy reference. So this is for a R minus 1th layer. As a vector, I am saying it. That is all. We are done with the whole story of narration of the previous class. The whole derivation is this much, all that we have done. Fine. Hope everybody is clear with it. It is simply W1 y1 plus W2 y2 and so on. Your derivation is with respect to W. So all you got is each time when you are taking with y1, with W1 only, that corresponding y1 will be there and so on and so forth. Fine. Can I move on to this class, new part of this class? Okay. Right. So this is the tricky part somewhat compared to this. You have to compute dou E of I by dou VJR. Okay. Again, what will happen now? Calculating E of I, where can you calculate E of I? In fact, at the last layer you can calculate, because that is the only place where you know what to expect and what you have got. So that is where you have to do your calculation there. Let us consider first case. We'll calculate this. Maybe I will just erase this part. Now it is clear to everyone. So I'll just erase this in the interest of having some space here. Let's do the calculation for R equal to L. That means in the last layer I am doing the calculation here. Okay. Now, how is E of I defined? This we have done. 1 by R, 1 by 2 times summation. How are we writing? E of I, let's say I could write it as M equal to 1 to, see, to calculate error, how many are there in the last layer? How many neurons are there in the last layer? KL. I need to go through each neuron there for all layers, correct? And I should look at what is the output that I am getting there. What would be at an mth neuron, right? And in the nth layer. And this is for a given input I minus, maybe I should be already knowing what is my y cap of I for that. And this square I am taking. Hope you all remember this function that we have written in the previous class. Or let me even just I am following the textbook, not even cap is there, y of I. So you know x of I and y of I sets, there are such n sets. This I correspond to one set, and finally you do this 1 over n kind of stuff there. Okay, summation over all those things. Right. So what I should do here is clear so far what I have written. All I have done is, yeah. See, at the last layer, what is the output getting as a result of your whole algorithm convergence? That is, in the nth layer, at an mth neuron, the output is YML of I. You know from the training data that should be Y of I. So I'm taking sum of squared differences. This is for one specific cost function we're calculating here. That's all I have written here. Okay. This summation E of I would calculate for all n samples, right, and minimize that essentially. Okay. This of course, this we have written E of I also. This, if you recollect, we were writing it as EM square also, where EM is difference between these two square. Okay, EM square is convenient in some sense, which you will see now. Okay, so let me take now, what should I compute now? Dou E of I with respect to dou V J L. Correct? I'm in the Lth layer. I'm computing it for R equal to L here. What would be that? How do you think I could bring YML of I into something Vj of L? Any idea on that? Can you help me with that? I want to express Ym subscript L of I in terms of something. Is it related to Vj? Yes. What is that? F of. Very good. Look at here how these are related. Yj is nothing but f of this. This is your, for example, this could be a simple step function or a sine function where -1 to +1 is there. So I could write it as f of, so let me write it here. This would be function of V mth neuron in the Lth layer, output you got for the ith sample minus Y of I whole square. Small mistake, this should end here, minus Y of I whole square, this summation. Is it clear? See, Yj is nothing but f of this V, whichever you got as a result of W1, Y1 plus W2, Y2 and so on. This is all you are doing. Why did I write like this? Because I have to take my derivative with respect to n, as simple as that. Now, without putting too many steps here, just by looking at that, can you, anyway, there is here 1/2 is there, okay? Summation m is varying from 1 to n is there, okay? Now you tell me dou E of I by dou Vj L. Can you tell me what would be that value? 2 and 2, this is gets cancelled. So it is like, then what will you get here? See, you are taking with respect to j, and this subscript can vary from 1 to n, but your derivative will be there only for m equal to j. Correct? So what will be that? The first 2 and 2 anyway get cancelled. That's why we have intentionally introduced this 1/2. Later we want to get rid of this baggage. So we included this baggage in the beginning. Okay. So f of V J L of I minus Y of I. Okay. F of V J L of I minus Y of I into what will I get here? F dash of V J L of I. Okay. This we are writing it as EM, for example, EM of I. So I will write it as, what will be then? E subscript J, because M is varying there. So I could write it here EJ of I into, I could write here I also, into F dash of VJL of I. This is my very important result. This now all I did so far is to compute this value for the last layer. EJ of I into F dash of VJ L of I. Just have an interpretation here, otherwise it looks just some variable names. What is it that you are doing? Well, if you have taken your f of x to be a simple, what was that function we have taken? Sigmoid function. It is equal to a times f of x into 1 minus f of x, correct? That is what will give you f dash. Your x there is v dash j L of I. What does that mean? Whatever in the output you got here, this is just a scalar which you have got there. This is a scalar that you substitute in that expression and you are going to get this. Clear? How do you get EJ of I? EJ of I is nothing but, you know what is the output at that point? This is the output you got. You subtract one from the other. Of course, there will be, this can be negative and positive depending on that only. Its evolution, in which direction it happens, will depend on. In derivative anyway, if one is more than the expected value, it should go in one way, less it should go in the other way. So of course, that's why that sign is captured here. So if we plan to give you a programming assignment where for certain number of layers you have to compute, so this has to be very clear to you. It's okay if you do not remember the sequence of steps and do it like I have to do on the board. There is no other way for me. But if you look at the textbook and understand step by step and know each term, that will serve your purpose. Is that clear? How to calculate that? See the way we are doing now. You know the output only at the other end. And there you are calculating, once you know dou E of I, dou J is nothing but summation of these for varying values of I from 1 to n. You should be getting that J there. You should be able to calculate that. Dou J derivative you are able to calculate. Once you know the derivative, you know delta W nu equal to W bar nu equal to W bar old minus mu into dou J by dou W. We have done. So this is dou J by dou W. We are calculating. Clear? There is one more last, what they call to the coffer. You put the last nail to be put to the coffer of this back propagation is there. That is to compute this for any value other than r equal to L. The idea is very simple. You could compute these values from the last one and somehow you use it to the next layer and propagate it to the other end. That is all we have to do right now. That's the last step. We are going to last knife into the coffer. That's what we will do, but just want to ensure clear, it is clear to you until this point. Yes. Where? Oh, sorry. This is a mistake. This M has to be K subscript L here. That was it. Good. That you do for all. See, this summation you are doing for all neurons in the last layer. So that is this M. 1 to KL. So last layer you have KL neurons are there, output layer. So you are looking at error obtained at each of those neurons and then summing up those errors. That's what you're, yeah. Please correct that. This is M. There is I sitting there on top again. That's a different one. Okay, good. So now let's do the calculations for any value of r less than L. Okay. So for the sake of convenience, now I would write it as r minus 1. That means for the first time you do is L is completed in your implementation. What you will do is r equal to L you takes. That means L minus 1th layer you will be computing at that point. So the way I would write it now is what is it that we need to compute? Dou E of I over dou Vj. Well, I should not write L here. Now let me do it for r minus 1th layer. This derivatives do, see, This I have to do for each R. Okay, R equal to L we have done. This anyway we figured out for all layers. There is no issue with that. This we have to figure out for each layer. R equal to L we have done. Let's say, let us put, I'm putting here R minus 1. Suppose R equal to L, if you substitute, then you are in fact computing it for L minus 1 layer. In other words, you are adjusting now the weights in the L minus 1 layer. In other words, okay. So how do I get that? So what I would like to compute is dou E of I over dou Vj R minus 1. In other words, I could call this as delta, right? Delta value for a jth neuron in the R minus 1 layer. Look at this diagram. This, anything in R minus 1, any neuron, you take any neuron here, it will have impact. Okay, this will have impact on all the other R neurons in the next layer. If I modify this, this will propagate to everything else in the next layer. That is clear, right? So we are looking at dependencies because you are using a chain rule and somehow you will be bringing it to the other layer. That's why we are looking at that. So how do I write this here now? This I could write it as, let's say, let me use even the notation in the same way that is there. Let me first write the expression for what I explained just now, and we'll again relook at that. This is written as K is varying from 1 to KR, dou E of I over dou V K R of I into dou V kth neuron in the rth layer by dou V. This will come J R minus 1 of I. It's very simple. R minus 1th layer, it has an effect on all layers in the rth layer. How many neurons are there? 1 to KR, they are there. So dou E I by its value, I'm using it K, kth neuron in R layer. Such things I am considering all of them here. Okay. And then of course, Vk of R of I by Vj R minus 1 of I. Fine. Is this chain rule the way we have written? Is that clear? Good. Do we already know something here? For let's say R equal to L you are taking here. This you know it already. This is what you have computed for the previous layer. How could I write this? Delta, which is the layer here? R. See, this is same as this, except instead of R minus 1, you have R here. So this is nothing but delta J times R, which you would be, for example, R equal to L, you take it. That you know by the time you are coming to the layer before that. You compute it and then go to the R minus 2 layer. Then this whole thing will be available to you. Hope you are following the rhythm here, steps here, sequence. Okay, so this you know, and all that we need to figure out is this fellow is the only one remaining for us now. If we do that, we are done with backpropagation. Dou Vk R of I by dou Vj R minus 1 of I. Okay. Any clue on how we should approach this problem? So let me write it as dou by dou Vj superscript R minus 1 of I into, how should I write Vk? Look at here. VKR, I have to somehow express it. What I would get here are VKR minus 1. So is it possible to write that? First you write, how do you express VKR of I? VKR of I is summation. I used a K here, so let me use M here. M is varying from 1 weights are there, na, W1, Y1. So M is varying from 0 because I want to take that bias also there. Okay. So I will take this as M is varying from 0 to, well, VKR. How many are there inputs there? KR minus 1. Is it not? See, rth layer, anyone in the rth layer gets inputs from how many neurons? KR minus 1, right? So KR minus 1, right? And then I have the weights, of course, for the rth layer, okay? And of course, this KM I should write. M is varying now for the kth neuron here. This is K. Hope I am not messing up here. Let me confirm that. Okay, so far so good. Into Y. The inputs are coming from R minus 1th layer, and there I am taking its mth neuron, and of course this I do for V of I. Is that clear to everybody? Very simple. See, W, this weights, if you recollect, you just write it in terms of R only. Do you remember that? For each one weights, rth layer means you give the superscript R. And now this, why did we keep K here? Because it's a kth neuron you are looking at. So K, this M is K0, K1 and so on. When this M is 0, this is 1 essentially. That's how the bias one we are taking. Is everybody with me? Hope you are not lost somewhere. Okay, good. So what is the next step? I'm sure it is very clear to you how I should proceed from here. I need to take it Vj. So what else should I modify here? Vj R minus 1. Can I write it in that terms? Yes, I can write it. That's all I would do now. This I would write it as dou by dou Vj R minus 1 of I into summation M is varying from 0 to K subscript R minus 1 W subscript Km in the rth layer, and this would be equal to function of V. I should take V coming from V for the R minus 1th layer, mth neuron of I. That's all. Okay, all I managed to do is, see, there are V values here looking from R to R minus 1. All I did is I managed to express this in terms of R minus 1th layer V. That's all we did, nothing fancy. Then I'm sure you should be able to tell me. So when will this have a non-zero derivative? When M equal to, that's all. Then what would be that? You take F dash here, correct? And that should suffice. Anyway, this will remain for that. So what would be that value? Can you tell me now? Substitute M equal to J here. That's all you have to do. So W K, I would get here M equal to J, and anyway it is in the rth layer. And of course I take first derivative of it, F dash of V J. Pay attention here. M equal to J I'm having. So M value also I'm keeping there. J. Vj R minus 1 of I. Correct? That's all. Then anyway Vm of R minus 1, that if I take it is 1, and simply all I need to do is substitute it here in this summation. Okay, so that implies my delta J R minus 1 is equal to, oops, it should not go so far. Okay, yeah, delta J R minus 1, I could write of I is equal to, anyway this doesn't depend on I, so I could just, yeah, well, it depends, so I could write it, nothing wrong with that. So that is equal to summation k is varying from 1 to kr. This is delta jr of I into this one. What is that value? This one. So, well, this has nothing to do with k. So, I will simply write here wkjr, okay, and I would write this f dash out, f dash of vj r minus 1 of I. We are done with it. So, you know delta jr we have computed for L, then you take r equal to L, you get it for L minus 1th layer. You take r equal to L minus 1, you get it for L minus 2 layer, so on and so forth. We are done with it. So just for aesthetic sense, you call this as, let's say, Ej of I. You are calling it there. He'll also call this also in a similar style. He'll be calling it. So he calls it as Ej r minus 1 of I. Okay. So that's all he is calling that. Anyway, the earlier one is Ej L of I. If Ej of I, you are calling it here just to look like the same thing. You have something multiplied by the derivative one, you are substituting there. So instead of Eji, this is, he is calling it as Ejr. It's just for some equations looking simple in a similar style. We are done with the backpropagation. So you will have an assignment, programming assignment, where we will give you a simple structure where you have a set of inputs, could be just two inputs, x1 and x2. It could be as simple as having an XR problem where you have two neurons. Okay, I could, for example, create more, like for example, I may do it in a way that I get, if I have three, see what is the purpose of my hidden layers. I will just, in each region that I have created here with these lines, the whole set of points should be separated into these classes, at least into these regions. Say, for example, I could have some points here, some points of this class here, and maybe some here, some here. If I could manage that within this, any of these things, if they are separated, those number of neurons are good enough to me. Say, for example, I have given you something like this. You will know that in your hidden layer, all you need is how many neurons? 3 lines, 3 neurons, 3 linear lines, 3 neurons. You will have 3 points there. Okay. In the output layer, I will just take 1 neuron. Then combining them, I should be able to do that. So if I give you that, then you have two levels of things are there. You compute the output at this layer, which you do it for r equal to L. You could do this computation. Then you, after that, you go to L minus 1th layer, do the calculation, adjust the weights, repeat this process until the change in weights. There are different ways in which you could put this constraint stopping criteria. One stopping criteria could be, for example, you look at change in terms of weights compared to the earlier one, how much change has come. You look at the norm of it. If it is too small, you could stop there, for example. What could be another criteria? You look at change in your penalty. What is your penalty term? J, this J itself, summation of E of I. You look at how much weight change is happening in that. So mean square error you are computing for every training sample. You are adjusting these weights such that this is getting minimized. That is another way you could do. Of course, there are few other types also you could think of, but these two should be more or less sufficient for our current purpose. That is how, that is when and where you stop it. Okay. See, all I did is, for example, I have considered here mean square error. Tomorrow, you may see that there are many other terms that you could consider here. A simple normalized cross correlation, let's say. Then from here, everything would change there. This derivation part will change, isn't it? Maybe the first part would remain same when it comes to when I did it for the two terms, that dou vk r of I over dou vj r minus 1 of I would remain same. But this part you need to know, then you should be able to derive it. So if you get used to one, then you could in similar lines you could do it for the other. So that's why this is, I would say this is important that you understand it. Although this is there in textbooks, although at the end of the scores and when you are doing projects, you may simply call the inbuilt functions and they will be doing a job for you. But you should not become handicapped tomorrow when you come up with some new function and then further you want to have your neural network work. So you should understand then where all these terms would change. For example, another very commonly used one is cross entropy. That is another term I am sure some of you might have come across in your communications and all. So if you look at, if you draw, how does cross entropy term would look like, where the last penalty that you would give versus the penalty that you would give for increasing values of the difference, you would see that when the error is too high, the rate at which your gradient descent converges will be lot for your the term which is based on, what did I say? I myself forgot, cross entropy term. Okay, so there are many instances where cross entropy would give you better convergence. Otherwise, it will be just oscillating there itself, because it doesn't look at the relative magnitudes. It is the absolute thing you are looking at when you are subtracting it here. But when the error is very high, the penalty that it poses, cross entropy, if you just see some videos on YouTube, there are many good videos that helps you to understand neural networks cross entropy loss function. You just take a look into it, you'll find many good resources. And most of you, all of you in fact, have a background in communication also, where you would have discussed in depth about this cross entropy term. The logarithm function is there within that, so that when you have a difference, is it looks at the relative magnitude and the slope at which your dou w, whichever the derivative is coming, that slope will be very high here compared to what you would get with a say, for example, that too when you consider the binary entropy 0 and 1, just two classes, you will see that there will be good number of instances where cross entropy will give you better results. So those are just two possibilities. If in segmentation, for example, in medical imaging, she is actually using dissimilarity somewhere, you would be using it. So these all you should be able to, if it is available, well and good. Otherwise, you should not move from PyTorch to something that is there in MATLAB, whichever is giving you that last function. If required, you should be able to understand, code the stuff. That's why we will give you that some experience with a small scale network. Means there will be a lot of issues when the network becomes too high. This is not as ideal as you are looking at the examples there. There are too many things you need to look into there. Okay, with that background to this, if it is clear, we will be done with this backpropagation, and I'll make few remarks before I conclude this lecture about this backpropagation. So is that clear, or any questions? Okay, so few more comments here. One I already made about the stopping criteria. I have already talked about that. And another thing I would say is convergence speed. Okay, if you recollect, W bar, maybe I will write here again somewhere. I will write on the top board. W bar new is equal to W bar old plus delta W bar, maybe this you call old or new, I don't care. That's the delta change you are doing. If you recollect this happens to be minus mu into that whole summation of I equal to 1 to n, right? Something like dou E of I by dou W bar. Okay, if there could be some mistakes, but that's the whole thing. So what helps you? The convergence speed is something related to mu. This also we discussed in a single neuron model. You take big jumps. Okay, you are hopping it, but your minimum is here. You have a long hop. You go there, you jump here, you go there, you jump here. You never converge there. Okay. So on the other hand, if I am making very, very small jumps, that might be minimum is somewhere there. Okay. I will take too long. So it's a trade-off. You should ideally know the behavior, which we should never know. There is no way you should know. But in principle, in the classroom, I can comfortably say that based on the shape you are expecting, choose it. Okay. As simple as that. In practice, you have to vary that and see when it is converging and what should be the case. Okay. Clear? That's another thing. That is the second point I wanted to mention. Third point, what is the algorithm that we are using here? Gradient descent. But in practice, you might use, there are better algorithms also. Okay, if we go to that, this will become more of a calculus class where gradient descent, steepest gradient, and all these methods you would be discussing. So those methods would probably either converge better or they are robust in some sense. So you would maybe go to something else. And again, another point is gradient descent is a local minima. It gives you a local minima. What do I mean by that? Suppose I have a function like this. Okay, if I am varying my x, okay, I should write here x. I got out of scope there, but it's okay. This is your x. This is your function value you are computing. Suppose your initialization is somewhere. It will go in baby steps. It will settle down here. It will try to move from here and realizes that that is too high to climb. So it will settle down here. It will not look at anywhere else. Suppose if my initialization, I'm randomly initializing my weights. If that ended up somewhere here, this will say that this is a very comfortable cave to be in rather than going anywhere else, and it can never see this. Then of course, only when my initialization here is somewhere into that pit, then only it will go there. So typically what you should be doing is try with different initializations. Okay, and with those initializations, each initialization, how is it going to help you? You are, for each initialization, you run this algorithm and you will be computing this minimum cost. If you are into that small pit, which is not local minimum, this j, that is the least j that you could arrive at. But there is one more thing. If you happen to luckily fall into that, that j will be much lesser than this, because that is converging even better there. Okay, that you could, this function is nothing but you could think of it as mean square error. Okay, this function is nothing but mean square error function, you could think of it. So anywhere here, if your initialization is in this region, that is the least mean square error you could get. This y is your mean square error. If you happen to initialize here, this would be the minimum. Otherwise, this is the minimum. So you try with different random initialization and choose that which overall gives you the minimum. Of course, you have to run the whole algorithm for that particular initialization. Is that clear? Right. Now, don't think that every time my function will have this nice kind of stuff. Okay, my function could also be this could be my function, also could be. Then what will happen? Look at this slope here. This is almost 0. So I will not move anywhere. Just I will be standing and dancing there itself. I will never come here. Okay. So that is where there is another term you use in addition to that, which is referred to as momentum term. This is what you would use in practice, a momentum term. So I will write the expression here for that. So for example, it would be something like this. My delta W bar, a jth neuron in the rth layer, the new value of that will be equal to alpha times my delta W for jth neuron and rth layer in my previous iteration, alpha times that, minus then all this blah 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 mu is there, I equal to 1 to n. Okay, my delta j subscript r of I into y bar of r minus 1 of I. And typical values of this alpha are, you empirically choose some value in between some 10% to 80% of your previous weights that you have got. Okay, the moment you are here, your slope is large here, you arrived here at this point. Now this delta W also, 80% of that value you still use here. You will not solely depend upon the derivative that you are getting at the current point alone. You carry how much jump I made in my previous step. Now it is telling me to jump only one step. I made a jump of 10 steps, okay, in my previous iteration. So, well, let me, if I had made 10, let me at least make, this is telling me 1, but I just made 10. It has been a big jump, that maybe there is a plateau here. So I will take, instead of 1, if it says I may do 3 now, I'll give some weight to my previous jump, delta W, and do it. And of course, this equation will be same. W bar mu is same, but instead of this is my delta W bar of mu earlier, that I will do alpha times my old jump, previous iteration jump, minus this would remain same. That is, this is referred to as momentum step. It is giving you momentum. And of course, this is a very vague way of, informal way of telling. It has really meaning perhaps to what you in physics you refer to as momentum. If you do it, it might have it. I haven't explored. If you are curious, you can have a look into that as well. Clear? So this is another step you could use. Okay, so maybe a couple of points I will make here and will leave you. In the training process, one approach is, I wish I have it somewhere. Yes, good. I will compute the error. This is again the same point I'm reiterating, which I told earlier for a single neuron. You compute the error over all neurons, sum it up. Based on that only, you will decide how much delta W you should make. This is referred to as it is referred to as a batch approach. Okay, this is referred to as batch training. Then you may repeat it over some number of iterations. The same thing you may do. Whatever you got, you take it as an initialization and you repeat the whole process. Then each of them is referred to as epochs. So after that, you repeat the whole process. There is another way also. Assume that I have some 10,000 samples are there for me. Out of this 10,000, I will randomly pick, let's say, 2,000 samples out of it. For this randomly picked up 2,000 samples, I will compute this and I will make a jump. Accordingly, I will make the delta W. After that, I will again randomly choose 2,000 samples from here, compute this, compute the derivatives, and repeat the whole process. This is also, again, this picking up 2,000 samples, calculating it, and arriving at one solution. That is referred to as one epoch. And after that, you again pick up 2,000 samples and do it. So that's another epoch. This is what in your graphs, and also if you started working or if you are going to work, you will realize that you have epochs. This is what epochs mean. The first one is referred to as batch training. Second one is referred to as stochastic training, because you are randomly choosing it. There is something else also called as online training. That means you perhaps are not, all the samples are not available to you. It's like students are coming at their own level. So as each student comes, we just train with that guy and adjust our weights. We don't have the luxury to randomly pick. So that's referred to as online training. So this is all the process of training. Hope that is clear. So these are the three: batch training, stochastic training, online training. Last point, this is all as far as training is concerned. Once you are done with the training, everything is fixed. Just that you, for a given input, you don't have to do this back propagation and all. You just need to look at the final values you are getting. So this is very convenient and comfortable to even put it into some hardwares or embedded systems of even small capability. Training is very memory intensive, computational intensive. But when it comes to testing, that's more convenient. And that's what you typically, that's why you see all these machine learning things, despite computational hungry, memory hungry, finally they can make a cut into even small embedded systems, because you have to there see, you could do all this training on a huge monster workstation or a server. You learn these things. Finally, you deploy it into some, because then you, if you look at the computation is pretty much down. You just need to W, all that is there is W1 J1, W2 J2, the W1 into Y1, W1 Y2s you have to do. Summations are there. Once the activation function has to be computed. These are the two important computations that has there. Okay, clear? We'll stop here. We are done with now backpropagation. We'll discuss other aspects of this classifiers in the next class. Okay, yeah.